Alrighty, let's now maybe first of all talk about your programming test number 2. I think that's really important. Let's clarify any doubts and then look at the instruction together. Don't forget, your lab number 4 will be due tomorrow. If you're having any trouble proving maybe the part number 2, I would say still submit your best attempt. And then I'm going to release as part of the solution to lab number 4, Andy recorded some video to walk you through also the proof step in that part 2. I can also release it tomorrow. You can also follow through. But I think before the deadline, it's so important for you to try on your own so you can see how you might get struggle during the test. I also released the practice test for your programming test too. Also tried it out, and then I'll give you the solution on Monday, maybe late Monday, so you can definitely get more time to try on your own. And your programming test number 2 will be next Wednesday, the usual time during your enroll session. And let's now take a look at the guide together, right? So if you go to the lecture site, and then you will see towards the end, you got your programming test number 2 guide. All right, let's now take a look. Okay, let's see which part might be more important. The same usual time, the same place, right? Oh, that's interesting. Okay, beg your pardon. I put the wrong version here, okay? I hope you didn't get confused. Okay, I'll fix it for sure, okay? I'm not too sure. Did I go to the wrong year? I'm pretty sure I checked. I might just go to the wrong year. I might just go to the wrong year, sorry. Sorry for the confusion. There we go. I went to the wrong link. That should be okay. Yeah, I'll be very scared if you, all of you move to WSC. Sorry about that. Okay, go to the site, and then there we go. That looks like the right one. All right, there we go. Okay, your programming test number 2, the same place, and 50 minutes. That's the best I can push before because we got a back-to-back, we have to leave 10 minutes before the next one. All right, policy, you can take a look, and then let's now go over, okay, this will be important for the grading criteria. So there will be also 2 parts for your programming test number 2, just like your lab number 4. So the first part will be, mainly you'll be given the problem description, for example, NAND gate, NOR gate, things like that. Or maybe something like what you were given in programming test 1, you know, the similar style. And then you're going to specify the corresponding context and machine. That's what you'll do for part number 1. It'll be roughly about 40% of the test, roughly. Oh, beg your pardon, 60%. Okay, I was looking at the wrong line. 60% for the first part. So that means even if you fail the proof completely, you can still get up to 60%, roughly. Okay, that's the intention. And then about 40% will be for part 2, meaning that once you have done with part 1, you're going to prove your part 2. So this one here, I would say there could be machine. So I would suggest maybe when you do a lab 4 and do the practice test, just get prepared. There might be machine. But format will be very similar to your lab 4 and practice test. Yeah. All right, so make sure you don't have any syntax error, and then there will be some penalty. And then the PDF event B summary will be available to you as last time. All right, so you can definitely look it up during the test. And the coverage for the test, I would say just study for lab number 4. I can even tell you, you don't need to worry about lab number 1, 2, 3. Lab number 4, focus on that.
Would you say the difficulty of the test is harder than the lab 4?
No, I wouldn't say that. I would say the actual test will be very similar to lab number 4. Very similar. Okay. Yeah. Also very similar to your practice test. Very similar. All right, and of course, you know, for any part about the math, functions, relations, if you want to review, doesn't hurt. I'll leave that choice to you. So that's why I said over here, optionally, if you want to review any part of the math, you can, of course, go back to the previous lab. And I still owe you the lab 3 solution. I'll make sure I post it, okay? I just forgot. And for your lab number 4, that's a primary focus. And the practice question has been given to you. And part number 5 over here, I would suggest to really make the best use of it. Let's say after you have gone through lab number 4 yourself, or even after going through the solution for lab number 4, you may want to set yourself a timer, maybe for 1 hour or even 80 minutes, that's okay. And just treat it like a lab test, and then go to remote lab, and then import the startup project of the practice test. It'll be the most valuable because you're seeing that for the very first time, and then try to solve it to see what you can have after the first try. Of course, you can try that for as many times as you like, and try to do this at least once before Monday when I release the solution. I'll give the solution to you by the end of Monday, right? So you can still have some time to look at that. Alrighty. All right, the link over here just for you. If you want to practice exporting the project for submission, you can do that too, right? Just in case you're not familiar. Otherwise, everything in the policy-wise, it will just be the same as a programming test. You will not need your mobile phone. It's not an E-class test. So please bring your physical photo ID, if possible, and then go there in time. If I can start earlier the test, I'll start earlier to give you extra time, like the last time. I'll try. Okay. Guys, any question you want to ask? All right, sounds good. Okay, let's now go back to the bridge. All right. So let's do a very quick recap. All righty. So last time we went ahead talking about inference rule. And the most important thing is remember how to interpret the inference rule. So given this particular inference rule with the antecedent and consequent, in order to prove the consequence, it will be sufficient to prove antecedents. And the L here is just label. All right, that's something pretty clear. And you guys can go over all the explanation about inference rule from the recording. It's there. And we talk about the syntactical difference between sequence and also inference rule. So you can think about A and C over here individually, they are sequence. There's only a single sequence over here. But there is a set of sequence in A. So it could be that we have a single sequence here. In order to prove it, we may be able to split into two independent sequences. That's one of the rules that we saw. I'm going to look at that to recap again. And of course, if you don't have anything above the line, it will be so-called an axiom inference rule. That will be the terminating case when you do a proof. Okay? And then for the sequence, individually, there will be set of predicates, right? Not sequence. Okay? Just make sure you don't get confused between the two, even though they're closely related. And we talk about how we can do some example proof, and usually you will be given some outstanding sequence to be shown provable. And typically, the sequence will come from the proof obligation rule that we actually talk about. And this will be just one of them from the invariant preservation. And starting with this, typically the very first step when you do a proof is to see which hypotheses are relevant to the goal I'm trying to prove. So for example, here, I have this particular goal I want to show provable. Only has to do with variable n. So I need to decide which hypotheses over here are relevant. For example, you can see this one only has to do with D, so I don't need it. This one here, true, it has to do with the n over here, but it's more about upper bound for n, which has nothing to do with whether n plus 1 will be natural number. Right? You got to make a choice, make a decision. It is certainly possible you may have found yourself either drop too many hypotheses or drop too few, so you can always come back. Okay? So monotonicity is always the first one. I wouldn't say always, but typically the first one. And after that, we got the relevant hypotheses and also the goal we want to prove. And now this case, it matches very well the piano number theorem number 2. Right? That's one of the example theorems in inference rule that we spoke about last time. You can see this guy here matches exactly this one. And this guy here matches exactly this one. And for this inference rule, it's a terminating rule because you can see above the line, it is empty. So, axiom. No need to prove any further. Any question? So today, we're going to see a more sophisticated proof for us to try. That'll be more exercise for us. Okay? You can look forward to it. All right, if no questions, let's move on to see anything else. Yeah, so this will be one typical proof step. You start with something with so many hypotheses, drop the irrelevant ones using monotonicity, and you start with this, much more compact. And then you have to apply a series of inference rules until you get to a point where it simply matches the pattern for some axiom inference rule. That'll be the terminating case to say it's proved. Okay. That's really important to understand that. Of course, sometimes it may be that given this particular guy, after monotonicity, you got something like this. However, rather than going in the linear order, you might go with a tree order, which is to say, in order to prove this, it would be sufficient for me by another inference rule to prove two sequences independently. And then you got to discharge each one of them independently. That's something we'll see today, actually. All right? So just don't get confused. This is not the only way you can prove something. There might be more than one way, but this is typical. All right, so we talk about the first set of example rules. We're going to see the second set today. All right? And we talk about these are the inference rule that's terminating the base case. And we talk about these, which are the recursive case. All right? You can refer to the recording from last Tuesday to really revisit. Let me just focus on one of them. The ORL is the more tricky one to really understand. So this one is saying, if I have a sequence over here, it would be sufficient to prove this one and this one independently instead. So if you want to make it more visual, this is what I want to prove, a single sequence. That's outstanding. It would be sufficient for me to discharge this one here and this one here separately. So each one of them individually will be a little bit easier because now I don't really need to consider a more complicated hypothesis, which is like a disjunction. I can consider them independently, either with P or with Q. All right? That's something we'll also see today, nicely. But you just have to know this one here. And reminder again, how do we know the naming convention for the rule? Okay. Number one, it says L. L means to the left of the turnstile. So we are saying that to the left of the turnstile over here, we have some disjunction, which is OR. That it is saying that. And we might see later, there is another one called, over here, ORR. That one is to say, now to the right of the turnstile, we got a disjunction. And when we got a disjunction as the goal, we can either choose to prove P or we can choose to prove Q. If you choose to prove P, in this case, it would be R1. If you choose to prove Q, it would be R2. All right, you really got to dive into the exact symbols in the inference rule to see. Question? You got to prove both, yes. It's not optional. Okay, it's a good question here. Let me emphasize. Whenever you apply ORL, like over here, when you split the original single outstanding sequence into two, sequence number one and sequence number two, it's not optional. It's not to say you want to prove at least one of them. No. You want to prove this and you want to prove this. If somehow you're able to prove only this branch and this branch is unprovable, the whole thing back here is still unprovable. Remember the interpretation. In order to prove this, it would be sufficient to prove this and this. So if you cannot prove this, then you cannot show that this is provable. Right? That's sensible. All right, any question? All right, if no, let's now move on. And then we try to also explain to you about the other two rules. You can refer to them. They are actually easier to interpret than the ORL. Right, this is pretty much the last page that we spoke about. Let me talk about what we said about this one here, and then why don't we do a few? Let me do maybe all of them together with you. I think you just need more exercise, more exposure to sequence. Let's now do this one. Okay, let me just go here and then interpret that. All right, for this one here, first of all. This one comes from MLN. MLN actually got some guard that's not there, which means implicitly it would just be true. So at the moment, MLN has no guard, which is an issue. That's something we're going to fix later. And we are trying to do about invariant preservation, and that one there has to do with n minus 1 is a member of n. And don't forget, the way we derive this one here is very important. We spoke about it in the earlier lecture. You want to review. So what we said was, number one, we take this outstanding sequence here, and we drop everything but this one that's relevant. So it boils down into, after applying monotonicity, to say, we want to say, given that n is a natural number, we want to prove that n minus 1 is a natural number. Obviously, that was unprovable because, as you said last time, if n is equal to 0, 0 minus 1 can contradict this. It's not a natural number. So this is unprovable. That means our original model is problematic. And the main problem is the antecedent over here is not really sufficient enough for us to show that n minus 1 is a natural number. One possible fix is to have n larger than 0 as the extra guard for MLN. That's something I'll show you on the slides. Once you actually add this guard to MLN and regenerate all the proof sequence, you're going to have this rather than true. You're going to have n larger than 0 over here to continue with the proof. And that one's going to make it provable. And I think one of you actually asked me before, like last time. This also is worth revisiting. Whenever you're given a model, right, with a static part and dynamic part, always you try to apply some proof obligation rule. It could be for invariant preservation. It could be for invariant establishment, which we'll talk about. Also, it could be for deadlock freedom as well. Any proof obligation rule is going to generate, based on the particular model, some proof sequence. So once you have got a proof sequence that's outstanding, you'll try to discharge each one of them. You will attempt to prove. If you find any one of the sequence that's unprovable, that means you have to go back to the original model and fix the model. So what do I mean fix the model? You have to see from the components of the sequence, for example here, you can see the components over here, this comes from the axiom, and this comes from the invariance, and the true over here comes from the guard. Any part can be fixed so that you can make the sequence actually provable. But you got to make a decision where to fix. All right, once you fix the model, here's important. Once you have fixed the model, you have to regenerate the proof obligation rule upon the fixed model. That one's going to give you the updated or revised proof obligations. And then you got to discharge each one of them again. If you're able to discharge them all, then you're done. And as I said, you can think about the analogy, like running JUnit test cases on your Java code. If you got a set of JUnit test cases run on your Java classes, if you got a red bar, go back to your Java code, fix something, rerun. If you got green bar again, done. Okay. All right. Why don't we try more proofs over here? Why don't we try this one here? Okay, this one here. Is this one provable though? What you gotta try is, somehow you can see we got n plus 1 less than or equal to d. Apparently we need this, we need n, and also we need d. Arguably, these two are relevant. D and n, they're both natural number. But I'll say this one here is even more valuable. This one talks about directly the relationship between n and d. So it turns out keeping this will be enough. All right, so I'm going to keep it. By keeping it, I'm going to apply monotonicity. Okay, apply monotonicity, and I'm going to get n less than or equal to d, turnstile, n plus 1 less than or equal to d. So this will be the new sequence. If I can prove this, it suffices to really show this original sequence is provable. All right? Now, is this provable though? Is this? If you don't think that's provable, give me some counterexample. Yeah. Exactly. Yeah. If n is equal to d, then it's not provable. All right? That's the intuition you can draw to yourself. Not provable because n might be equal to D. That's pretty good. And notice that this outstanding sequence over here comes from ML out. And at the moment, we also don't have any guards for ML out. So that means implicitly, we got some true over here. So let's picture ourselves. If we want to, well, having some events without any guard, in general, is an issue. You don't want the event to be enabled all the time. How can we add some guard to it so that it can help the provability of the sequence? So we're going to do something very similar as this one here. So for this one here, when we find that this sequence is not provable, we try to strengthen the hypothesis by adding some guard to MLN. Now we're going to do something very similar. We find that this is not provable at the moment. If we can somehow add something to it so that the guard over here can be put to something other than true, which will effectively adding some hypothesis over here that's going to make the whole thing provable. What should we add? Yeah, n plus 1 less than equal to D or n less than D, either way. Uh-huh. Change the antecedent, you mean over here? Yeah. Okay, let me add a guard first and I'll answer your question. Okay, so what we can do is, so here, we may have a new guard for ML out. Right? It would be n strictly less than D. So this one's going to be very useful because if we got this guard over here, n less than D, in that way n plus 1 will be mostly equal to D. So we're good. Okay, now back to your question. You don't really want to think about modifying this antecedent directly. You more want to think about this part over here comes from the axiom. If you want to modify this part, then you got to change the axiom. Do you really want to do it? And these parts comes from the invariance. Do you really want to fix the invariance? That's the question. And this part here comes from the guard of ML out. Do you want to fix it? I'm just suggesting alternative. I'm not saying this for this particular sequence to make it provable, adding guard is the only solution. That's not what I meant. So in this case, the reason that we want to fix the event right away is because the event itself is already unguarded. It makes sense to make it guarded first. Okay. In general, let's say in the exam, if I give you some unprovable sequence like over here, I might say, now fix the model so that you can prove everything. Now, if I didn't say which part you may want to fix, you can choose any part you like, but you got to be sensible. Mm-hmm. Good. Yes, go ahead.
So, are you saying that if we change n greater than n less than equal to D, so we'll be changing one of the invariant which will be applied to all over the model?
No. When we change, okay, notice one thing here. Okay, let me be very clear. So what I said was, if we add this guard over here, n less than D, what I meant was, okay, I'm going to add it to over here, n less than D. So let's look back to the proof obligation. Oh, it's actually in the next page. If you recall, this is the proof obligation we had earlier, right? So think about axiom is here. Invariance is here. And the guard over here is, we talk about ML out. It's simply just no guard, just true. So if you actually add just the true over here, it's only going to impact the proof sequence related to ML out. So it's going to be ML out, invariance 0, 1. And also in ML out, invariance 0, 2. Only two of them. The other two remain the same. Okay? Did this kind of answer your question? Yeah, my point is, over here, if you're only fixing the guard for ML out, it's only going to impact 2 of the 4 sequence. On the other hand, when we add a guard over here for ML in, we're also going to impact the other 2 proof sequence separately. I'm going to summarize this in the next page, but for now, I'm just sketching the idea for you guys. All right, this is another unprovable sequence. So far, this is what we have got. We got this sequence over here, unprovable. The resolution to it is adding a guard to MLN. Also, this one here is also unprovable, and the way to resolve it will be to add a guard for ML out. So that's what we have got so far. And let's now try to prove the other two. Let's see what we have, okay? How about this one here? Oh, sorry. Okay, how about this one? Do you think this can be proved? Well, of course, you got to decide in the first step which hypothesis do you want to drop and keep. This one has to do with n plus 1 is a natural number. What's the relevant variable? N. Apparently, either this one here or this one or both should be kept. Not this one. This one here, arguably might keep it, but it seems like this one here is already enough. Because if I know n is a natural number, n plus 1 should be a natural number as well. And this is according to the piano theorem over here, P2. All right, just for your information, right? That matches exactly that. However, I want to show you a common mistake, okay? Would it be, so now we know this is ultimate thing we want to get into by dropping the hypothesis only down to here only. But let me show you something that will be wrong. Okay, let me show you that. If I simply say this sequence over here is proved by P2, because I'm thinking that this part over here implies this part. If I show you that, that's my proof. No, that's wrong. Simply because, based on the rule here, the goal, I agree, it is n plus 1 is a member of n. However, you can see the hypothesis over here is only n is a natural number. You do have n is a natural number, but you also got other stuff. So that's strictly speaking wrong. You cannot apply that rule just yet. Okay? So if you simply say this directly, that's wrong. Because too many irrelevant hypotheses. What we should do instead is by dropping all the irrelevant hypotheses first. I want to only keep this one here. That's all I want to do. So the correct proof should be to say, number one, by applying monotonicity, I will get n, a natural number, turnstile, n plus 1 is also a natural number. This will be the correct proof. And once I get to this sequence over here, I can claim that it matches completely the P2. So now you can see this one here matches this one here. And this one here matches this one here. Okay, it's a subtle difference you have to watch out. P2. All right, any question? So the main message from this particular proof is telling you, when you actually want to conclude, you actually got you don't want to do it prematurely. You want to do it maturely by after dropping all the irrelevant hypotheses. That's the main lesson here. Okay. Question? Yes.
On the programming test, are you gonna give us proofs which are not provable?
You mean programming test or written test?
Sorry, the programming test. That one.
Oh, for programming test number 2.
Yeah.
So I would say what we're discussing right now about the bridge controller is not directly related to programming test number 2. Right. I would say for programming test 2, it's more about doing more about rodent in that particular domain of example. So for that one, focus on lab 4 and practice test. And this one may be more relevant to your written test number 2 and exam. Mm-hmm. Yeah. All right. Why don't we do one more just to be complete? Guys, how about this one here? This one's interesting. Okay, this one can also help me make a point. This one here, I can tell you something here. You can see that. How about this? I'll give you a little bit hints. Can you please compare this one here, that's outstanding, and the decrement rule? Would you agree they kind of look similar, but not exactly, right? What do I mean? If I look at the decrement rule, number one, the antecedent must be n less than or equal to n. I do have that. And on the consequence over here, the goal, I got n minus 1 less than n. But here I got n minus 1 less than or equal to d. Not exactly. So you cannot say P2. Sorry, you cannot say decrement directly. It's wrong. So if you say decrements directly, so it's proved, no, not the case. But it's something we will want to massage the sequence into. And this is something I would like to show to you. And this is something that we don't really have a inference rule to talk to be referred to. But this is something I will call basic arithmetic. Okay? I'll put it down first, and then I'll explain. ARI is a special term you can feel free to use during the exam. Whenever you believe that you can do from one into another based on basic arithmetic, you can do that. But you better actually explain what do you mean by basic arithmetic. Because sometimes when you say it's basic, it may not be agreed it's basic. It may be just wrong. Right? So you want to justify. So here we are saying that when you got less than or equal to d, I can do the following. I can say here, n, whenever I got p less than or equal to q, it is equivalent to p less than q or p equals q. That's obvious. So after this basic arithmetic, I can turn the sequence into the following. I can turn that into, so I don't drop anything just yet. So d is a natural number, n is a natural number, and also n less than or equal to d. And then I got n minus 1 less than d. Let me just get a little bit more space for myself. N minus 1 less than d, or n minus 1 equals d. Would you agree? Number one. So here, I'm not using any of the inference rule that we introduced last time. I'm using basic arithmetic. So I would say in the exam, specifically, if you believe you can actually turn some condition into another one using basic arithmetic, number one, you can just use ARI. However, you should always put down some explanation like here for me or the TA to understand what you're doing. All right? ARI is very convenient, but it comes with a risk. You better make sure you don't have too big a jump in ARI. Okay? And once we have got this, what would you say we should do? Yeah. You can use OR. Okay, sure. Okay, I agree. So now should we use OR1 or OR2? Well, for this example here, it's easy because I only give you OR1. That's the only one you can choose. But in the exam, you got to judge by yourself, right? Okay. So guys, what I'm asking is this. Let me be very clear to you. If you recall the rules we have, what's the difference between OR1 and OR2? Given the same disjunctive goal, if you apply OR1, that means you want to leave this one here and drop this. If you choose OR2, that means you want to prove this but drop this. If we go back here, between this guy here and this guy here, which one is going to be useful for getting closer to decrements? R1, yes, good man. Exactly, this one here. All right, so we want to keep this one. All right, we haven't really applied any monotonicity just yet, but we can do that in a moment. Yeah, I'm going to highlight it and take question. Yes?
So if I was to write it like n minus 1 equal to d or n minus 1 is less than d, so in that case I will be using R2.
That's correct. That's correct. It's a good question here. Yes, I agree. Because when you actually do ARI, it is possible you may rewrite it as this one comes first or this one comes first. Depending on which one you choose, R1 or R2 may be applied. You're right. That's correct. Good question. All right, so now after this, let's now do that. So we're going to apply OR R1. That one there is going to give us the natural number n less than or equal to d, and then turnstile n minus 1 less than d. Okay, we're not done just yet. So after this, let me tell you, we're getting very close. You can see this part over here is corresponding to this part here. And this part here is corresponding to this part, right? But we cannot apply it right away. We got to drop these two. Okay? So I'm going to say a final one, monotonicity. Sorry, I'm running out of space. I'm going to put it exactly here. All right? But you'll see on the slide. It's also on the slide. So after this, we're going to get n less than or equal to d, turnstile n minus 1 less than d. And that one there is just another sequence over here. And after this, we can apply decrements. And that's it. That's the proof. All right, so now we have done all the 4 sequences. And in conclusion, these two have been shown provable. One for ML out, one for ML in. But these two have been shown unprovable. One for ML in, one for ML out. Our resolution would be to add one guard over here for ML out and add one guard over here for ML in. That's our resolution. Yes? That's very good. Yes, yes. That's exactly right. Because we kind of discharge all these 4 separately in the first go. So that's why at the moment, when we actually do this one here, when we do this one here, and when we do this one here, we don't really consider new guards just yet. But when you regenerate all the 4 sequences, they will be there. But it's okay. Adding more hypotheses is fine. You can always drop them by monotonicity. Good. Alrighty. Any questions about this? All right. If no, why don't we do something very quickly? And then I think I'll try to at least finish these 2, and then we'll take a short break. Okay. Now, the idea would be we're going to improve our events. Based on this unprovable sequence, I'm going to make a green. How about this one here? Based on this guy here, we're going to fix MLN. So when we go to MLN over here, we're going to add a guard. And the guard is going to be when n larger than 0. Add one guard. We fix the model. And then we'll try to, based on this one over here, we're going to add this guard here. And based on this one here, we're going to add an extra guard. D and less than D. So now, because we have fixed the model, what should we do now? If you recall the workflow, once we have fixed the model over here, we should regenerate all the 4 sequences. All right, good. Let me just do a little bit copy and paste. So the way I'm going to do it is like this. Okay, if I may. Okay, let me do a little bit of, sorry, I should have prepared this before the lecture, but let's not do it quickly. Let me just copy this page. Okay. And we're going to regenerate. And first of all, the question is, how many do we have? 4, the same. So 2 from the guards, and also 2 from the invariant condition, the same. The only difference is we're now going to, oh, actually I have it here. I beg your pardon. I thought I didn't have it. Okay. So now the difference is, you can see now we got extra here. N larger than 0, N larger than 0 versus N less than D, and also N less than D. Right. I'll make some annotation for you. So this is the new guard for ML in. And this is the new guard for ML out. All right? I would suggest when we go back to the beginning here, this one here is already provable. Now we're just adding some extra hypothesis. It should be easy. You just drop it by monotonicity, which is okay. And for this one here, that was also provable before the fix. And by adding another extra guard over here, that's also fine. You can just drop it. It still be provable. Now let's now revisit these two, which was not provable. Let's do these two together. Okay, these two. So I'm going to do this one here and this one here. But for these two, I would still suggest you do as exercise. And you can also check the solution on the slides. All right, let's now do these two. Why are they provable now? So which one should we do first? Yeah, we can do this one first. Or even better, let's see where we got stuck. According to before, we're going to apply monotonicity first. And then monotonicity, we will be able to now use that new guard. Okay? And once we get to the new guard, we should be able to discharge it. Okay? Let's now take a look. Let me see some slides. And then we can come back here. All right, so this is something that's unprovable. So that's why we've got to strengthen the guard. And you will see this is another one that's also unprovable. So that's why we've got to also strengthen the guard. And then we fix the design. Right, so that's a new guard I just mentioned. Right, we got new ML out. Also, we got new ML in. Okay. And we got to regenerate all the sequence again. And we'll try to prove each one of them one by one. Okay, for this one here, this one used to be proved, so we don't need to worry. Okay, but it turns out we just drop more hypotheses to make it provable. All right, this one here, we still get the same P2. All right, this one is no trouble. And how about this one here? That one was not provable before. ML out invariant 2. Okay, so this one here is basically this one here. That was not provable. Let's try with this one first. So I try to stay a little bit closer to the slides. So when you study, you can see both. Now, how do we discharge that bottom left corner? Okay, we'll start with this. And notice that we do have the extra hypothesis over here, n less than d. All right, that's important. And first of all, we apply monotonicity to drop all the irrelevant one. And apparently, we should keep this one here for sure. That's really the point of adding that extra guard. And we get this. All right? N less than D, N plus 1 less than equal to D. Turns out, this just matches the increment rule. How? Let's go back. All right, let me just show you that. You just need more exercise, right? That's why I really want to spoon feed you a bit in the beginning. All right, so for this one here, we're going to apply monotonicity over here. And then we get n less than d, turnstile, n plus 1 less than or equal to d. And based on this, you can see n less than d correspond to n less than n here. N plus 1 less than or equal to d correspond to n plus 1 less than or equal to n. So that's why we can apply increment. All right. Pretty straightforward. And then we are going to do the next one. All right, let's see this one here. All right, this one here used to be not provable. So that was the MLN invariant 1, which is here. So I'm talking about this guy here. This guy here used to be not provable, right? You can see it was not provable before. So now with the guard over here, how should we prove it, right? Let's see some quick slide, and then I'll write it down. Monotonicity, again, what should we keep? Well, apparently, we want to keep this guy here, right? That's a new guard. Otherwise, what's the point? So we're going to keep the guard over here, and then we still got n minus 1. Now, what should we do? Which rule should we apply? It turns out it's just a P2 prime. All right? So that'll be the last one. So we're just going to drop everything. So not here. Monotonicity, which we're going to get n larger than 0, turnstile, n minus 1 is a member of n. And this one, you can try to see, it matches exactly that. I'll leave the check by you. This one here exactly matches this one here, right? So we're done. So after fixing the 2 guards, now we got all the 4 sequence related to invariant preservation proved. All right? All right, any question here? All right? Just get the big picture clear. Don't get too much lost in the detail, and just make sure you can do the proof. All right? Okay, I would suggest, why don't we take a very short break by taking attendance, and then we'll continue. Okay. Let me pause the recording. Okay, we are almost done with the initial model, which is great. We'll finish that on Tuesday, but I would suggest we got about 20 minutes or so. Why don't we do the following exercise? Now that we are now more into the proving mode, why don't we try some more sophisticated proof right away and see if we can work it out, the solution. Okay? And I would suggest the following. Let me present this to you. Oh, of course, I'm going to switch. Sorry about that. Let me switch in a moment. This one is actually generated by one of the proof obligation I will talk about maybe on Tuesday. But why don't we try to prove it directly? That could be a proving exercise for you. Okay, guys, this one here. Okay, so this is the deal. You don't need to understand how this proof sequence comes from. It is simply some outstanding sequence we want to prove. Can you actually try to prove it? Sorry, this is what I meant. This is where I want to go. Not that one. That was unprovable. Okay, this one here. Can you actually try to prove this one here? Oh, don't worry about DLF. It's something to do with deadlock freedom. But given this, are you able to discharge it? All right. How about this? I would suggest I'll give you guys maybe 2 or 3 minutes of just to sketch a little bit to see how far you can go. And then these are the rules you will need to really help discharging it. Okay? And then I'll give you about 3 minutes or 4. After that, I'm going to go over the proof with you so you can compare mine with yours. Okay? 3 minutes or 4. And we're going to go over it together. If I may give you a hint, but if you don't want it, don't just pretend you didn't hear me. you may want to do some arithmetic on this guy here. Help you a little bit. How about that? You can say by arithmetic, this guy here, we know from the previous example, it is n less than d or n equals d. Okay? And then we can say now, by the arithmetic, I got this. Okay, how about this? That'll be the first step for you. That will help. So what we have done, basically, is turn this guy here into this guy. That's it. One thing you can think about, for example, here you can see we got some disjunctive, we have some disjunctive hypothesis. And it somehow matches this guy here, right? So you may just want to try, maybe by using this rule, I can now somehow split this sequence here into two. And for the half where, for example, you got n less than d as the hypothesis. And I can choose to prove this one only, ORR1. Now I got hypothesis and goal just the same. This one somehow matches this one. Even though we haven't talked about it, I can see the pattern here. We got hypothesis and the goal matching. All right, this is how you can prove one side. Okay. Okay, which just gradually lead you to the solution. But you can definitely feel free to redo it. Okay. All right, let me move on a little bit. Okay. So now, by monotonicity, it turns out this is the only hypothesis I would need in order to make progress, ultimately. So I can drop everything else. So I'm going to have n less than d or n equals d. N less than d or n larger than 0. All right? By dropping all the irrelevant hypotheses. Again, how do I know? Because somehow I know the solution, so I can tell you. But of course, when you do the exercise yourself, you got to experiment a little bit, like how I did it for the first time. Yeah, question? D greater than 0? Okay, sure. The way I see this is like this. You can see, if I just got this alone, I know that this is a disjunctive goal. Disjunctive hypothesis. According to ORL, I will be able to somehow split this into two sequences over here, which we'll see. One of them is going to use this one as hypothesis. The other one is going to use the second hypothesis in isolation, which you're going to see. In the case where I'm only using this one here, you can see this one matches one of them. And I know that if the disjunction is the goal, I can choose only one of them to prove. So now this one here and this one here really match each other. That one just matched the hypothesis rule. Of course, it need more practice. I know. It might seem a little bit too much in the first, but we're going to keep practicing. Yeah?
So you say that for the goal, we just take it from one up.
That's correct. For the hypothesis, okay, here you can see we got disjunction in the hypothesis. We got disjunction in the goal. Now, for the disjunctive hypothesis over here, you cannot drop any one of them. The best you can do is to consider them separately in isolation by splitting them. On the other hand, for the disjunctive goal, you're basically saying, I want to prove either this or this. If I can show you either proof, that's good. Right. All right, let's now move on a bit. So now let me now apply ORL. Because I got disjunctive hypothesis over here. So I'm going to split that into two hypotheses. All right? Oh, I really meant to say here, right? Disjunctive hypothesis. So now one of them will be n less than d, and then n less than d, or n larger than 0. Okay, that's one of them. So you can think about this one here and this one here. All right, and the goal remain the same. And I got another sequence to discharge, which would be n equals d, turnstile, n less than d, or n larger than 0. Another sequence. And this one here matches this one here, the other hypothesis, and also the goal is the same. Okay. In order to discharge this, I would suggest we leave that for a little bit later, but we can leave this for next time. But let's now get this one done. All right. Now, how do we go further with this? For this one here, you can see this n less than d matches one of the goal. You're basically saying P implies P, almost like that. In order to do that, we need to make sure we drop the irrelevant one. And we can do that. This is according to ORR1. When you got P or Q, you can drop the Q. This is exactly the Q that we are talking about. Okay? So let's do that. So now we got ORL. And then we got n less than d, and also n less than d. Sorry, let me write a little bit better. Okay? So now this one here will just match the hypothesis rule. This is to say if P appears on both sides. In that way, you're done. So you can think about the H over here, it's just empty, like a true. So that one's okay. It will still be considered as matching. All right? So now this will be hypothesis. So this particular branch is done. However, at this point, we still cannot claim that this particular proof is actually done until we're actually done with this branch over here. All right? Question?
Isn't ORL between that last blue box and the green?
OR.
L. And then between that.
Yes,
and the
yes.
pink one.
I just got it wrong. Yeah, I agree with you. I'm not sure what I'm thinking. Absolutely. So when we get to this part here, it's definitely ORL, for sure. And then when we get to this one, since we're choosing this one here only, so that'll be ORR1. Thank you. Absolutely. All right, so for this one here, when we come back on Tuesday, I'm going to show to you how to do this. We just need one more inference rule to learn, to get it. I think it will make our later life easier when we want to discharge the deadlock freedom. But I think we do that part first today. All right, any questions? All right, what should you do over the weekend if you want to do some study for 3342? All right, number one, you want to make sure you go over lab number 4 and try the practice test. That will be immediately relevant for your programming test number 2. But I would suggest also try to start reviewing about inference rule and how you can prove sequence style is going to be very relevant for your written test 2 and exam. You want to get prepared earlier. Okay? Any question? All right. So today we're going to end the class earlier. All right. Thank you.